All right, let's jump right into this. Welcome to today's explainer, where we're going to tackle a massive and, honestly, sometimes really intimidating topic: American structural code mastery. Look, whether you're a brand new civil or structural engineer, or even if you've been around the block a few times, you've probably felt that initial wave of panic when staring down the absolute alphabet soup of American structural codes. I mean, you've got IBC, ASCE, ACI, AISC, ASTM. Literally, if you printed them all out, you'd probably need a whole separate engineering degree just to design a bookshelf strong enough to hold them. But don't worry, our goal today is to completely demystify all of this. We're going to map out this entire ecosystem so you can navigate it like an absolute pro, totally headache-free.
So here is today's game plan. First up, we'll decode that alphabet soup. Then we'll explore the overarching frameworks and invisible forces at play. Third, we'll get into the actual physical building blocks. Fourth, we'll examine the crucial details and connective tissue holding everything together. And finally, we'll synthesize the whole shebang and talk about a very dangerous software trap you need to avoid. Okay, kicking things off with Section 1, the alphabet soup, dismissifying the acronyms. It's so common for fresh engineers to feel completely overwhelmed by this on day one.
So let's just address the elephant in the room. With all these acronyms, IBC, FASC, ACI 318, AISE 360 flying around the office, who is actually creating the codes we use? Do you know who develops these standards? And maybe more importantly, do you know why totally different organizations are responsible for completely different parts of structural engineering? Well, there's a huge trap fresh engineers fall into right out of the gate. They kind of mistakenly think there's just one giant American code master book that they have to memorize cover to cover. There absolutely isn't. Memorizing code numbers, that's a complete trap. The real professional approach is understanding the ecosystem. American structural engineering is actually this interconnected web of highly specialized professional organizations. So when a senior engineer asks what standard governs a design, you shouldn't just rattle off a single acronym. You need to understand the whole chain of how these standards talk to each other.
Moving right along to Section 2, Frameworks and Invisible Forces. Let's look at how these individual rules build into the big picture.
At the very top of our ecosystem umbrella, we have the ICC, the International Code Council, and the IBC, which is the International Building Code. The absolutely crucial point here is that the IBC sets up the broad, overarching building code framework. It basically answers the big question, what overall building requirements apply here? We're talking occupancy types, construction classification, fire protection, means of egress, all of that. It's actually really fascinating because the IBC doesn't give you the detailed structural math. Instead, it's sort of like the ultimate traffic cop, pointing you directly toward the specific standards that do have the math.
And that points us right to the invisible forces acting on our buildings. Enter ASCE 7, published by the American Society of Civil Engineers. This is a brilliant standard. It details all the minimum design loads your structure has to resist: wind, earthquakes, snow, rain, your dead and live loads, and exactly how they all combine. The mindset shift you need here is massive. Your job isn't just to blindly punch a wind speed into some black box. You really have to understand the specific hazard, evaluate the site exposure, determine the resulting pressures, and literally track that load path all the way to the structural response. All right, Section 3, the building blocks. Now that we've got the framework and forces down, let's step out of the theory and look at the physical reality, the concrete and steel. If you're designing structural concrete, ACI 318 by the American Concrete Institute is your go-to. It covers it all: flexure, shear, torsion, slabs, foundations. But listen closely to this. Please don't just treat ACI 318 as a massive, boring collection of equations to memorize. That's a rookie mistake. Instead, use it to really understand structural behavior. When you look at a concrete member, ask yourself, what is this actually doing? What specific failure mode am I trying to prevent here? Once you answer those behavioral questions, then you ask what the code requires to prevent it. That's much, much stronger engineering thinking. Now, for structural steel, we turn to the AISC, the American Institute of Steel Construction. AISC 360 is your general spec, but depending on your project, you might also need AISC 341 for seismic stuff or AISC 358 for pre-qualified moment connections. And this just brilliantly highlights our ecosystem concept again. If you're designing a steel structure, don't just ask what section passes. Any computer can do that. As an engineer, you're empowered to ask the deeper questions. Why does this member work? What limit state governs? And how does this force safely make its way down to the foundation? Oh, and speaking of steel, I've got to give you a quick but super vital warning here. ASI, the American Iron and Steel Institute, is the standard for cold-formed steel.
Think light-gauge framing, wall studs, roof systems. Cold-formed steel behaves entirely differently than the conventional hot-rolled structural steel we just talked about. A major mistake young engineers make is assuming that, steel is steel. It absolutely isn't. Different manufacturing processes mean completely different design philosophies.
Section 4. Details and connective tissue. We've got our big materials, but how do we actually lock them together in the real world?
Think about it. Let's say we've designed our steel members perfectly on paper. How do we specify the physical material the fabricator actually needs to buy? It's a fascinating split. AISC tells us how to mathematically design the steel, but ASTM, the American Society for Testing and Materials, tells us what physical material we are using. When you see an ASTM designation on a drawing for a bolt or a steel beam, it's not just a random serial number. It's dictating the exact material properties, the specs, and the testing required for that real-world component.
And how do we permanently put those pieces of steel together? We weld them, right? This is where AWS D1.1, the structural welding code, steps in. Imagine your AISC mathematical design is absolutely flawless, but the connection is poorly welded on site. Well, you still have a massive structural failure on your hands. AWS ensures your connection isn't just designable on paper, but that it's fabricatable, inspectable, and actually safely constructible, because a connection is never truly complete just because you finish the math.
Now, keep in mind your specific projects might bring entirely different, super specialized codes into the mix. Doing a parking structure? You'll need the PCI handbook from the Precast/Prestressed Concrete Institute. Or if you're stepping away from buildings to do bridges, you're going to be living inside the ASTO LRFD standards. A building engineer spends their life in IBC and ASCE 7, while a bridge engineer spends theirs in ASTO. It's basically a completely different engineering dialect.
Finally, Section 5, the synthesis and the software trap. Let's bring all this theory together and confront a huge pitfall in our industry.
Let's run through a really quick practical exercise. Say your senior engineer assigns you a steel warehouse to design. Don't immediately open your software. Let's see the ecosystem work in harmony. Need the overall building requirements? Go to the IBC. Design loads? That's ASCE 7. Steel member design? AISC 360. Material specification? ASTM. And the welding? AWS. See how perfectly they all lock together like puzzle pieces? When you let the code answer specific engineering questions, everything just clicks. Now, there's a saying in the industry that I find to be incredibly true. Software can calculate a wrong model very quickly. This is the software trap. Far too many young engineers treat programs like STAAD, ETABS, or SAP 2000 as if the software itself is the code. It is not. Software just implements provisions based on the assumptions you feed it. Your job as the engineer is to ensure the underlying model is correct long before you ever trust those colorful results popping up on your screen. So what's the actual real-world workflow? Step 1, establish project requirements and codes. Step 2, determine loads and structural system. Step 3, analysis and member design. Step 4, detailing and review. Step 5, construction. Notice exactly where software fits in here. It only comes into play during Step 3. That is long after your core criteria, your governing codes, and your load paths are firmly established in your head. Look, if you're feeling a bit overwhelmed by all this right now, take a breath. You do not need to master all of this on day one. Here's a solid roadmap for you. Start with your fundamentals, mechanics, and materials. Then master the frameworks and loads. Only after that do you move into main materials like concrete and steel. From there, tackle the specialized codes, and finally, dive deep into the software and real-world projects. It's all about systematic, step-by-step mastery. Let's do a quick recap of our key takeaways from this explainer. Remember, American structural engineering is an ecosystem, not one single massive book. Make sure you know who does what. Let the code answer specific engineering questions rather than guessing. And above all else, the golden rule. Don't memorize. Learn to navigate. If you know how to navigate this ecosystem, you can design absolutely anything.
We've covered a huge amount of ground today, all the way from the broad IBC umbrella down to the granular, fiery details of AWS welding. So, I want to leave you with a question to chew on. Which specific organization or code from this alphabet soup do you want to decode and completely master next? Think about your weak spots and dive right into that part of the ecosystem. Thanks so much for joining me on this explainer. Stay curious and keep building that mastery.